do as example of centric buckling. Then we are going to carry out, then I'm going to teach an extension of Euler's formula. Don't worry, not too much equation, pretty straightforward stuff, okay? So last week, this is the what I copied from on Friday, okay? I just took the example across. You have this already, okay? So we are going to complete this example. So just to quickly recap, the column of 6 meters effective length is to be made from 3 plates as shown. Using Young's modulus of 200 gigapascal, determine the factor of safety with respect to buckling for centric load of 16 kilonewton. So given those information, we know that the effective load is 6 meters as written down there. And then we are aware that the load applied is minus 16 kilonewton, minus because in compression. We have to determine, or the question asks us to determine the factor of safety. And the factor of safety formula is P critical divided by Px. For us to calculate, so Px over here, this is known, okay? So it's known is a given value. What we don't know is what is the P critical, the critical load where buckling will occur, okay? The formula we're going to apply is P critical is equal to pi squared L squared divided by 8 EI. And we assume that Px will always be what? Online or inline. We're not online. Inline to the centroid. Okay, and anyone not sure what does it mean? Inline means what? If this is the centroid, the green thing is the centroid, the load that we are applying will always come down what? In line to the what? Centroid. Are we clear? This is the assumption we make. And we know in real life it seldom happens. Unfortunately, there are a lot of models around. It's just an approximation for now. Okay. Then an important thing to take note is we have to construct our transformation. Okay, so this is our transformation X, Y, and Z. And I'll tell you why this is important. Okay. So we sketched this figure out last week. Okay. And we look at buckling. So for this case, for the first case that we did on Friday, we sketched buckling. In the, can you put this downward? In the XZ plane. Okay. So the first figure that you see down here, buckling occur in the what? XZ plane. And when that's the case, last week I did explain that the YY is the second moment of area is taken about IYY. Okay. Why IYY? Because if you look at the curvature of deformation, it's the same as RY. RY referring to here. So this is the RY rotation, the RY rotation, the curvature is the same. Are we clear? Okay. Now, the next thing, there's another possibility we don't know yet. Okay. There's another possibility that buckling, now this is new. Okay. Buckling will occur in the XY plane. Okay, so there's two possibilities. So what do I mean by XY plane? Based on the transformation that we have drawn, I always emphasize on the transformation. It's very critical over here. So now this is our X, and this is our Y, and then this is rotation about what? About Z. Okay, that is rotation about Z. So I'm going to sketch how buckling will occur now. So now this is our structure. Structure is built in one end. And then this is our structure, same height. Right? And then I'm going to sketch our centroid. So centroid is in green. Okay. And then there's another possible deformation that will occur. And can you see the difference with the diagram on the left-hand side and the right-hand side? Yes or no? What is missing? What did I not draw? The dotted line, yes or no? Right? So you all know where we are looking at. So from here, the deformation will look like this. I'm going to draw the deformation pattern now. The deformation pattern now will occur like this. Okay. So when this is the case, what we see now is the critical load now. The PCR now is equal to pi squared is still the same. Young's modulus is still the same. Over L squared is still the same. Now, understanding the concept, what's happening in the XZ plane, can anyone tell me the second moment of area is about which axis now? Yes. So now it's about IZZ axis. Are we clear? Right? So this is very similar to what? When you learn bending moment, yes or no? Okay, now I will quickly recap what you learned in bending moment. Okay, so in bending moment, you also have what? Depending on the how the moments are applied, you can use either one of the second moment of area. Let me quickly recap for you in your bending moment. Okay, so now you guys have learned this before, but I want to remind you. Okay, so I want you to take note. This is IZZ. So just now we are going to recall. Unsymmetrical centric bending. When we have unsymmetrical centric bending, what do we mean? Remember, it's nothing to do with the what? With whether the left-hand side is equal to the right-hand side, or depending on the stress field. Okay. So now if I have a transformation running this way now, so this is my X, this is my Y, and this is my Z. Now we have a beam. The beam is running in this orientation. Hey, Eugene, draw properly. So now this is your beam. The beam is built in. Okay, so our beam is built in. And then I'm going to draw this is moment about Y. There's an applied moment about Y. And there's another applied moment about Z. Okay. And then x-axis, we have nothing. Okay, so based on right-hand rule, this moment will go this way. Beg your pardon, to apologize. So we will go this way. Okay. So these are all your moments that you see now, right? So the first thing to take note that the formula for this is what? So what we are going to calculate is stress in the what? In the x direction. Okay, we're going to look at normal stress in the x direction. And we realize that this will be equal to what? Will be equal to my over what? Okay, which axis? Second moment of which axis? You're right. Divided by I, multiplied by what? Z, plus or minus moment about Z divided by what? I, Z, multiplied by what? Y. This is the easy part, okay? So this is just a quick recall. So moment about Y divided by I, Y, moment about Z divided by what? I, Z. Why do we do that? Okay, why do we do that? Okay, so why am I going to relate this? Because this is, we can relate this to what? To our buckling. Are we clear? Okay, so if we were to look at our deformation pattern, so now, okay, we draw our transformation in the XY plane. Okay, in the XY plane. So when we look at our XY plane, what do we see? We see this. Yes, we see this. Okay, then I'm going to draw the vector moments. This will be our moment about Y, and this will be our moment about what? Z. And I want you to draw for me, this is rotation about Z. Okay. Now, how can you sketch for me how will the structure deform at this view moment of Y? This is important, okay? We're going to use this concept from week 3 until week 12. You have to grasp this concept, okay? I want you to blindly apply just a set of formulas without what? Visualization. Now, question for you again. If we look at this view, how would the deformation look like? Anyone? About Y, not about Z. How would the moment look like? Yeah, but can you see anything from this view? No. Okay, you cannot see the deformation about this view. Why? You guys look real gloomy today. What happened? Weather or the prof being an ass? Which one? Weather or me? Tell me, okay? Don't do that. Okay, thank you. Okay. 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 Stop sleeping, yeah? I love you guys a lot. I need you to focus on this, okay? So now, if moment about Z, how does the deformation look like? Smiling face or sad face? Good. Now I see smiling face. Come on, this is so exciting. I must be psycho if I'm the only one so energetic about it. Okay, yeah, Eugene, we know you're psycho anyway. So we know deformation will occur which way? Will occur this way. And if you look at the curvature, is a curvature in the same orientation as Z? Yes or no? Yes. So this is where you take the moment about what? You take the moment about IZZ. Are we clear? Right? So you look at the what? You look at the curvature of what? Deformation. Okay, so this will help you. If you forget the formula, this is what you must rely on. Are we clear? So now we have a different view now. Now we have a different view. We are going to view it from the X Z plane, and then we have rotation about what? rotation about y. So now our structure look this way now.